Welcome back to Lean Together 2026. Next, we have the pleasure of hearing Joël Riou talk to us about homotopy theory in Lean.
So I would like to thank the organizers for giving me this opportunity to speak about the formalization project that I've been working on throughout all the year 2025. That is about homotopy theory, both for topological spaces and simplicial sets. So I'm doing homotopy theory using the homotopical algebra from Quillen. So this is a kind of axiomatic homotopy theory. And it works for certain categories. So my goal, the formalization I did was to construct such structures. So you don't need to be afraid about the number of fields here. I'm not going to go into the details of these axioms, but that's the goal, is to construct such structures. So in a model category, you have three classes of morphisms that are called fibrations, cofibrations, and weak equivalences. So the data part is in the three first lines. And then you have a bunch of axioms. And you see the cofibrations, for example, appear here as a cofibration C, which is a class of morphism. So you consider the whole class of morphisms. And also in some assumption in certain axioms, like if you have cofibration AI, or weak equivalence I, or fibration P, this is a one way to refer to the status using type classes to say that a certain morphism satisfies certain properties. We also have trivial cofibrations. So trivial cofibration is an intersection of cofibrations and weak equivalences. So we have a bunch of axioms. We have finite limits, finite colimits, certain stability properties, CM2, CM3. We have lifting properties that I'm going to talk a little bit more about in a few slides. And we have a factorization axiom, two factorization, CM5. Any map can be factored as a trivial cofibration followed by a fibration, etc. So you don't need to know anything about this because I do not have time to go into all the intricacies. I will try to be as concrete as possible. So in my formalization, the main results are that there are I have constructed two model category structures on the category of topological spaces and simplicial sets. And one of the results is that they essentially define the same homotopy theory. So in the language of Quillen, we say that these two structures are what we call Quillen equivalent. So it's quite a huge amount of code. So after Flory's talk, I found out that about 7,000 lines of code were blank. So it was such a disappointment for me, but so you can find the code. I will give the link in the Zulip after the talk. And so, of course, it's abstract homotopical algebra, but there are some serious mathematics involved in there, and there are some quite concrete consequences. One of which was mentioned in Anna's talk yesterday, where she mentioned CW complexes, and she mentioned Whitehead theorem. So in this context of model categories, there is an abstract Whitehead theorem, and if we apply it to the model category structure on topological spaces, what we get is that if we have a weak homotopy equivalence between CW complexes, so which means that we have kind of bijections on homotopy groups, then it is an homotopy equivalence, which means that there is a map in the other direction with homotopies, etc. So that's my formalization, but I cannot cover all the aspects, so I will focus on kind of the difficult parts and the most challenging parts of the formalization. So first, I need to introduce the notion of lifting property, which is very important in this homotopical algebra. So in any category, we say that a morphism I satisfies the left lifting property with respect to morphism P if for any commutative square, there exists a lifting, like a diagonal map which makes both triangles commute. And equivalently, we say that P has a right lifting property with respect to I. And in homotopy theory, many classes of morphism can be defined using such lifting properties. So one is the notion of Kant fibration between simplicial sets. So in this talk, you don't need to know what is a simplicial set. Let's just assume that these are kind of combinatorial objects in order to model homotopy theory. So morphism is a fibration. So this will be part of the three distinctive classes of morphisms for simplicial sets, the fibrations. So they need to have the right lifting property with respect to what we call Horn inclusions. So delta n is the standard simplex. And we can do pictures. We have something like what we call the geometric realization. We can transform these combinatorial objects into topological spaces. So this is one way to visualize a standard simplex delta 2 of dimension 2. And a horn is something like this. It's a union of codimension 1 faces, but one. So you see there is a missing edge here. And topologically, you can see that this inclusion is a deformation retract. And this is one of the very few real homotopies that I had to construct in this formalization project. So in particular, a simplicious set that is that has which says that the map to the terminal object is a fibrillation is said to be a Can complex. So this is for simplicious sets. And for topological spaces, we also have a notion of fibrillation that was introduced by Serre, actually historically a little bit earlier, in 51. So a map is a continuous map between topological spaces is a fibrillation in the sense of Serre if it has the right lifting property with respect to the geometric realizations of all inclusions. So here I am putting bars to say that I am considering topological spaces attached to simplicious sets. So this is one way to define Serre fibrations. And so we have this geometric realization functor, but it has a right adjoint, which is called the singular simplicious set functor. If you have a topological space, you can turn it into a simplicious set, which happens to be a Can complex. This is something that I had to verify. And it is very similar to what you do when you define singular homology. So it's a quite huge object combinatorially. And so a map is a self-fibration if and only if this map of simplicious sets is a Can fibration. So this right adjoint functor, the singular simplicious set functor, preserves and reflects fibrations in these two categories. And then in my formalization, so there are a few difficulties. There is some abstract nonsense, but there are some core difficulties. One of which is to show that the geometric realization functor, which is the left adjoint, also preserves fibrations. So that's one of the main difficulties in the formalization. In my formalization, it was a story for quite a long time. So it's a theorem by Quillen, 67. Actually, the first published proof is by Quillen. So the geometric realization of a fibration between simplicious sets is a Serre fibration. So the contribution of Quillen in an article that is only 2 pages long is to say that we can assume that P is what we call a minimal fibration. So that's a stronger condition that we put. And it's completely a crazy condition because it implies that, in particular, if you make the base change over any simplex, so if you kind of assume that, for example, that B is just a standard simplex, then what you get is a constant fibration. So you have a one space F and you take the product with the base. So in that case, it is relatively easy to show that the projection is also a projection from a product if you work in the suitable category of compactly generated spaces, maybe as it was mentioned by Anna yesterday. So you get, if B is just a standard simplex, this is just a projection from a product, and then it's easy to show that it is a Serre fibration. So that's only the case where B itself is a standard simplex, and then in the proof, we may assume that B is a finite simplicious set, and the idea is to do some induction starting from the case of standard simplices, but then we go into a lot of technicalities. But what we can show is that these maps are topologically, with some caveats, but I don't want to discuss technical details. Essentially, this is a topological fiber bundle. So locally on the base, you have a projection from a product, and so it is a Serre fibration locally on the base. So the argument is very beautiful. The proof is very beautiful, even though I do not like very much the way it is the exposition in some references, but the argument is very beautiful. But it was very hard to formalize because you have to work with so many variables at the same time. You have commuting cubes with certain faces are push outs, certain are pullbacks. You have so many variables at the same time. So it was very tough to formalize. And also there is a lot kind of topology involved and combined with category theory. So there is some difficulty here, but then what I want to talk about more is the following theorem. So we know that our map is a self-vibration locally on the base, and we want to show that it is a self-vibration. So this is this statement, which say that if a map is a self-vibration locally on the base, then it is a self-vibration. So, and this is something which must have been known or trivial for people like Serre or Cartan, but it is actually even mentioned in some books, and they dare to give an outline of a proof. But for formalization, it is much more difficult. So in the book by Gabriel and Zisman, which is very much a model in terms of mathematical writing, in terms of clarity and precision. So even though it was translated from French notes, so there is a little bit that was lost in translation. It's a wonderful book. Let's look at their proof. So they use a slightly different definition of self-vibration. They use a cubical definition. So here you have the inclusion of a face instead of the inclusion of horns in standard simplicity. So that's technical detail, it doesn't matter too much. And here is the proof. So they say that the notion of a vibration in the sense of Serre as a local character with respect to the base. So they explain what this means, and the proof starts from the word indeed. Indeed, if F and G are the above maps, we can subdivide. So similarly as in Floris talk, we also have subdivisions into cubes, small enough so that F maps each cube of the subdivision into an open subset U of B, such that P minus 1 of U is a vibration over U. So this is very clear what we have to do here. We already have lemmas in Madlib which say that if you have a subset of the cube of a small enough diameter, then the image is going to be contained in one of these open subsets. So that's very fine. And the half part is just one on half lines. And just one word actually, we can then define gradually on the cubes of the subdivision an extension H of G. So you start from a face of the cube and then you have to extend starting from cubes that are near the face, and then you have to fill in everything. So I considered formalizing this exactly this way, but at some point I decided, no, I will go more I mean, I am kind of scared of topological spaces, so I decided to do a more combinatorial proof, to put as many combinatorial ingredients as possible. So instead of small cubes, I have used small simplices. So I have used the subdivision functor on simplicial sets. And following mostly an article by Jardine for this subdivision functor, because this article gives a lot of technical details that are kind of put under the carpet in the early literature. So it was very convenient to have a quite precise reference. So let's look at some of these details. So there is this subdivision functor, which is a functor on simplicial sets to itself. And it commutes with colimits, and it has a right adjoint, which I am not using very much. So it is essentially defined by its action on standard simplices. So let's look at its action on delta 2, the standard simplex of the dimension 2. So it is the following. And you may imagine how it would look in a higher dimension or maybe in lower dimension also. So what happens is that there is a vertex here in the subdivision for any non-degenerate simplex in the original simplicial set, roughly speaking. So you see for each vertex remains a vertex, but I also have more vertices coming from the centers of the edges and the barycenter of the main two simplex in delta 2. So of course, topologically, the geometric realization are the same. So which is a lemma that I had to prove. You have to prove that these six triangles glued together give something that is homomorphic to the original triangle. And you have to do it, of course, in the same, in any dimension. So it's not too hard because you have finitely many closed subsets. It's easy to glue them, but some technicalities and some combinatorics is involved. But the references actually contain most of the important observations, so that it was very satisfactory to do that. So the fact that we don't change the topological space is a quite general fact. Actually, it's a very general fact, but I have proven it only under a certain technical condition. So you do not change the topological space by replacing a simplicial set by its subdivision. So also, the subdivision functor is something that you can iterate. So if you do it once, you can do it twice, etc. So here you see the six simplices here are slightly smaller. And then if you iterate, you can make them as small as you like. So this is what replaces the first part of the argument in the proof by Gabriel and Zismo. So let's now look at the word gradually, the second part of the proof, and which is much more involved here. And here we need a notion which is very critical in the study of simplicious set, which is the notion of anodyne extension. So this is a class of morphisms between simplicious sets that are obtained as a closure of the family of Horn inclusions that I've mentioned before by certain operations like coproducts, push-outs, retracts, and transfinite compositions. So last year in Lean Together 2025, Jack McCoon's mentioned, referred to similar notions in the context of quasi-categories. And so there is some intersection between our works in some in the study of these anodyne extensions. And one way to characterize them also is that these are the maps that have the left lifting properties with respect to Kahn fibrations. And Kahn fibrations were precisely the maps which had the right lifting property with respect to Horn inclusions. So this is the way it is done. And the most scary part of my formalization, the statement I was the most scared about initially, I knew I had to prove this. If I wanted to make my variation on the proof my Gabriel and Zisman work, I had to formalize the proof that the class of anodyne extensions is stable under subdivision. And one corollary of that, when we have proven everything, is that the subdivision functor preserves weak equivalences. So it's quite non-trivial mathematical content. And so, of course, to prove it, it suffices to do it for Horn inclusions. And here you show that not only you get anodyne extensions, but actually you get strong anodyne extensions, which means that you do not need retracts. And here, actually, you don't even need transfinite compositions or coproducts. You just need finite compositions of push-outs of Horn inclusions. So these are the rules of the game. You can finitely compose such morphisms, and you need to find a way to obtain this morphism in this way. So let's try to do it for n equals 2. So this is an Horn inclusion from the left to the right, and let's subdivide it. So we need to show that this is an anodyne extension. So the first thing we do is we attach one edge. So this is allowed by the rules. And then we have two edges here connected by one vertex. Can you see my pointer?
Yes.
Yeah, so that's good to know. So then from these two edges, I can attach, I have a horn, so I can attach a two simplex. I can do the same on the right. Same here, same here. Here I am stuck, so I am adding one more edge. And I have two remaining two simplices. And that's a visual proof of the fact mentioned here for n equals 2. And this was the status of my understanding of this until maybe June or July last year. And I was very fortunate to find a wonderful paper by Sean Moss, who kind of gives a combinatorial description of all the solutions to this game. So it gives a combinatorial description of strong anodyne extension, and it shows that it can provide such combinatorial data for precisely this problem and a few others that are relevant both to some other aspects of the formalization and also to the formalization of functor quasi-categories, mentioned by Jack McCoon last year. So this is mostly what replaces the word gradually in the paper, in the book by Gabriel and Zisman. So let's now prove the main lemma. So what we want to show is, assuming that we have a map, continuous map of topological spaces, P from E to B, we want to show that it is a fibration, which here means that it is a Serre fibration. This is what we want to prove. And what we assume is that we have an open cover U by certain open UIs. And we assume that over these UIs, we have a Serre fibration. That's what we want to show, that we assume it is true locally on the base. We want to show it is true globally. So we need to find a solution to all such lifting problems. So of course, our assumption is that this holds if the image here of the map on the bottom is contained in one of these UIs, but we want to show it in general. So what we do following the strategy that was announced before is we apply the subdivision functor. So in Floris, subdivision of cubes, you have different layers of subdivision. But typically, when you want to subdivide cubes, you can subdivide in one time. You can get cubes of diameter less than epsilon. But for simplices, you need to do it. You need to iterate the construction. So here we apply the subdivision functor d times, a certain number of times. But we don't change the diagram in the category of topological spaces. So let's look at the adjoint diagram in the category of simplicial sets, because I would favor working in the category of simplicial set because I am scared of topological spaces. But if we make D big enough, what we get is that we can assume that all the simplices, so a simplex can be represented by a morphism from delta M to our object. We can assume that the map here, the composition to Sing B, it corresponds to a map from the topological simplex of dimension n to b. I can assume that it is contained in UI. So for any simplex of this subdivision. And so by our assumption, if I consider a horn and I consider a lifting problem like this, there will be a solution. So that's our assumption. And then if we look at the middle map, so it is obtained by iterating the subdivision functor applied to the horn inclusion that we have here. So it is going to be an anodyne extension, and even we can show it is a strong anodyne extension. So here, this map, vertical map, is going to be a finite composition of push-outs of morphism of the form like the one on the left. So gradually, we can define our lifting starting from the map on the top. And this is the way we get our lifting. So this is an overall strategy of proof of this lemma. So there are some technical details, but that's the overall strategy. Okay, so that was one of the main lemmas, very difficult results that I had to formalize in this process. And the goal was first to show that there is a model category structure on topological spaces. So the lemma I've mentioned before is not involved here, but so in a way, I have kind of avoided working with topological spaces. The strategy was to do everything with simplicial sets as much as possible. So I've mentioned that if I have a topological space, there is an attached CAN complex, which is a singular simplicial set attached to it. And so I see the homotopy theory of topological spaces kind of as a particular case of the homotopy theory of CAN complexes. So if I can provide definitions and prove lemmas about them, I can deduce results for topological spaces. So I defined the standard objects, which are the fundamental groupoid, homotopy groups, the long homotopy sequence of a vibration, and a very important lemma which characterizes vibrations between CAN complexes that are also weak equivalences in terms of lifting properties with respect to all monomorphisms, in particular the boundary inclusions. And this translates into a similar lemma for topological spaces, which is exactly what was missing in the first serious attempt at formalizing this model category structure by Reed Barton. So I was able to obtain this property that was missing in his work. And here I have done it in a very combinatorial way. So then once we have this homotopy theory of CAN complexes, we can essentially easily get the model category structure on topological spaces using abstract nonsense, including the small object argument, which was first formalized also by Reed Barton in 2018, and which is now in MATLAB since 2024 in my interpretation of it. And so I want to insist that in order to get this model category structure, I have shown almost no results about topological spaces. Basically, I had to show that we can apply the small object argument. So there are some technicalities involved. And Reed Barton's formalization was an inspiration for how to do it. But yeah, so but then everything becomes much more difficult, as you have seen in the previous slides, if we want to get this model category structure on simplicial sets. And there, I had to show a bunch of both combinatorial and topological results. So it was very involved. And yeah, so one of the difficulties of this formalization is that you cannot rely on a single source. I have admiration for people who can do blueprints. So I have not done any single blueprint for that because I had to discover on the way how to do things. My main reference was a textbook by Gers and Jardine, because this is also the book where I learned these things some years ago. And I had to go into a bunch of sources, but because also it's interesting to look at the original papers sometimes, etc. But I want to say how significant was the work by Sean Moss. It was very decisive in my ability to formalize the main lemma that I have mentioned. So I will conclude here. So I would be happy to answer any question, whether it is directly related to what I have talked about, or whether more generally about homotopy theory, of topological spaces, simplicial sets, or the more abstract general setting. Thank you very much.